This video shows an application problem involving the computation of the present value of a general annuity. This is the problem. Planning for their daughter's college education, the Woods opened an account paying 6.3% compounded quarterly. A payment of $200 at the end of each month are to be paid out of the account for 3 years. Starting 7 years from now, how much did the Woods deposit? So this is the question, and if we read well the question, we notice that there is a time in which there is no payment, so there was just the question is how much to put here at the beginning. Then after 7 years, they are going to start withdrawing $200 at the end of every month, and that's happened for 3 years. So this is what we have. So the idea of computing this, and the question is how much they deposit, how much the Woods deposit here at the beginning of these 7 years. So the question is, what is the amount at that point that I'm showing here in the line? So this point, how much here? But we notice that there is a time when we don't have any annuity, so there is just a deposit that is earning interest, and then after that we're starting an annuity. We call this a deferred annuity. So this is an annuity when the payments occurs after a deferment period, after a time. The idea will be this. I'm going to compute first what will be the present value of this annuity at the beginning of these 3 years. So this amount here. And we know the formula of the present value. This the present value equal the payment, and then 1 minus 1 plus I to the power negative n divided by I. So we know that this is the formula, but this amount will be the future value of this period here. So the present value of the annuity will be the future value of the deferment period. So let's compute first this present value of the annuity. So what information we have? We know that the payments are $200, so they are going to receive $200 at the end of each month. It's easy to notice what is n, because this is the number of payments. In an annuity, the n is always the number of payments, the total number of payments. So we want to know what is the total number of payments that we are going to use here in the formula, and this will be easy because we know how many payments per year, and we notice that the payments are at the end of each month. So there will be k equal 12 payments per year, and I symbolize as k the number of payments. These payments happen during 3 years, so the number of payments will be these 3 years multiplied by k, multiplied by 12, so it will be 36. So the I is the periodic rate of interest, but we have here the nominal rate of interest, so the interest in a year is going to be 6.3% compounded quarterly. I'm going to take notice of this. R equals 6.3%, and it's compounded 4 times per year. It's compounded quarterly, so M equals 4. So we need to take into account this, because if we notice that the payment per year that are 12 is different to the conversion periods per year, so we are in front of a general annuity. To compute this periodic rate of interest, we need to find the equivalent rate of interest compounded monthly. So we need to compute this I that is given always with this formula. I equal 1 plus the nominal rate of interest divided by the number of conversion periods per year to the power the number of conversion periods per year divided by the number of payment per years, M over K in this case that I'm using these symbols. So minus 1. So please use this to compute I, and this is the I that is going to be in the formula. So this is the equivalent rate of interest compounded monthly in this case, because K equals 12. That is equivalent to this 6.3% compounded quarterly. Okay, so let's make the computation. Let's put everything in the formula. You use a calculator, and when you use a calculator, you will notice that the periodic rate of interest compounded monthly. So this is the number that I'm going to put here. Just make a substitution in the formula. We know everything. We know R is 200. We know N, that is 36. And we know I, that is the number that we have computed already. So put it in the formula. And then use a calculator to compute this. I already did it, yes? 200, open bracket, 1 minus, open another bracket in your calculator, 1 plus. It will be a good idea if you put this number in the memory of your calculator. I explained in another video how to do it. So, and then also how to use it to compute this present value. So you can do that, and you notice that the present value of this annuity, so the amount here at this point, is going to be 6,548.11. So this is the present value of this annuity, but this is actually the future value of this period, this 7 years period. So they need to put here some amount at the beginning of these 7 years that allow them to have 6,548.11 at the end of these 7 years. After that, it will be withdrawing every month $200. Okay, so let's compute the present value of this period now when we know that the future value is this 6,548.11. Okay, let's do that. So we have the future value for this period. So for this period, we have that the future value is 6,548.11. So to find the value of this account 7 years before, this will be the future value, 6,548.11. We are going to use this formula, per present value equal future value 1 plus I to the power negative n, when this S is the future value of this period. And this n is the number of conversion periods in this. There is no payment here. So actually the n in a formula of compound interest is the number of conversion periods. And the number of conversion periods in this case will be n, and it's easy to compute because it will be 7 years and the interest is compounded quarterly. So it will be 7 times 4 if we want to know the number of conversion periods. Okay, let's use this, and we know that for this period the future value is 6,548.11. So let's type here 6,548.11. Then the I, the nominal rate of interest is 6.3% compounded quarterly, so M equal 4. So the periodic rate of interest I here will be 6.3% divided by 4, or 0.063 divided by 4. And then it will be 7 years multiplied by 4, because this is compounded quarterly. So in this case, it will be 7 times 4 equal 28. If I make a substitution of everything in the formula, we know that the present value will be 6,548.11 multiplied by 1 plus this 0.063 divided by 4, and to the power negative 28. Again, use your calculator for doing that. So the answer will be 4,227.51. So the books will need to deposit 4,227.51 in this account. 7 years later, they are going to have 6,548.11. And after that, at the end of every month, they will be able to withdraw $200 every month. So this is a way to solve this problem. There will be another way to solve this problem, because we already compute I that maybe is in the memory of your calculator. We can use this I also instead of this. So remember the formula say here I, periodic rate of interest, and this is actually a periodic rate of interest every quarter. But we have another, remember, when we were solving this annuity that we have at the end, we used the fact that K, the number of payments, was 12 per year. We can use the periodic rate of interest compounded monthly that we computed previously. This will be good because sometimes we have this number in the memory of your calculator. and maybe it will be easier to use the number that we already have in the memory. So for that reason, another way to solve this problem is take into account this. So we noted that the periodic rate of interest compounded monthly is this, and this was compounded monthly. So if we are going to use this I here, it will be okay, but take into account that we have now the number of months, because this is compounded monthly. So you have this alternative, then you take into account that the number of conversion period taking into account this periodic rate of interest will be 12. Then n will be 7 times 12. 7 times 12 is 84. So if we put this 84, this I here, and the s that we have, the future value that we have, we are going to get the same answer for sure. Let's do it. So we put the 6,548.11, open bracket, 1 plus I, so 1 plus this number, that this is 1.00522676 to the power negative 84. If you do that, put it in your calculator. Maybe this number is already in your memory, or the memory of your calculator, so you don't need to do too much. So you press enter and you're going to notice that the answer will be the same. And this is the two ways of solving this problem. So this second part have two possibilities. You can use the actual interest given in the problem, or you can use the periodic rate of interest that was computed in the first part of the problem. But in this case, you will need to use as the number of compound periods the same number of the payment periods. Okay, with this I finished to explain this problem. I hope you have found it useful. Thank you.